Okay, so today we're looking at extension 2, integration by substitution. Our learning intention is to gain the knowledge in using substitution to integrate a function. Now, in extension 2, most of the time you will need to find something to substitute. So they won't give you the substitution, you need to find some variable to substitute. Okay, we'll be successful if we can determine what to use to substitute, especially in extension 2. So usually you have the derivative of a function, and that's within the function itself that you're trying to integrate. Otherwise, you might get something like this, where you have either sine squared x or cos squared x, and you have to use the identity that this is equal to a half 1 minus cos 2x. Use t formula, tan equals x over 2 for integrations in the form of when you have a cos and a sine being added together, or like a trig function, cos or sine, being added to a constant. That's when you're going to use tan x on 2. And then use standard integrals from our formula sheet. Which are those that are listed on page 3 of our formula sheet, and they're all here. Okay. Let's do some examples. Here's an example where we have we want to integrate e to the power of square root x over square root x. So usually something like this, we have a power, they're kind of similar. I'm going to use let u equal square root x. Okay, so then du over dx is a half x minus a half, which is written as that. So that dx is 2 root x du. Okay, so we're going to integrate, so that's going to be u divided by u, and dx is 2 square root x du. So maybe what I'll do is actually leave that as square root x. Yeah, because that will cancel out this. So really what we're trying to find as is 2, the derivative of e to eu. So take out the constant, try the derivative of eu du, which is eu plus c. And now resubstituting back in, we get 2 e to the power of x plus c. Okay. Here we have inverse tan x plus 1, and then we have x plus 1 all squared plus 1. Okay. In this case, I'm going to this is kind of like the curly bit, so I'm going to let u equal inverse tan x plus 1. So du over dx of inverse tan, well, that's on our formula sheet. So if we look down our list, it's page 3. So inverse tan of fx is the derivative of fx. So the derivative of x plus 1 is 1 over 1 plus all that squared. Okay. This will work out nicely, because if we then find du, we've got 1 plus x plus 1 all squared du is equal to dx. Okay, so if we want to integrate, so that's now u. We've got x plus 1 all squared plus 1 multiplied by 1 plus x plus 1 all squared du. Okay, well, that is just that. Yep, just written around the other way around. So this technically cancels out that, leaving us u du. So the integral of that would be u over 2 squared plus c. And so u is inverse tan, or arctan, x plus 1 over 2 plus c. Okay, that one worked out very nicely. Now, the good thing was, obviously, in extension 2, they're going to give you a question where something will work out nicely to cancel out. Okay, that's the aim. Okay, so here we've got cos x, and we've got 1 plus sine. What I'm going to do is I'm going to let the denominator be u. Okay, so if I differentiate this, the derivative of sine x is cos x. 1's a constant, so that disappears. So technically, du over cos x is equal to dx. Okay, so we can integrate. Cos x is on the top. Okay, this is all u now. Well, dx is du over cos x, and that's what I'd like to cancel out, leaving me basically the integral of 1 over u du. Well, 1 over u is just log of the absolute of u plus c. Resubstitute that back in for what u is. So we get 1 plus sine x plus c. Actually, we don't need the c because we actually have these actual variables. Because I've replaced this back, I'm going to jump back here and resubstitute these values in, because we have a definite integral. So that's actually log 1, I'll actually write it out, 1 plus sine pi on 2 minus log of 1 plus sine 0. Okay, well, sine 0 is 0, so that's just going to be minus log of absolute 1. Okay, sine of 90 should be 1. Yeah, so that's going to be log 1 plus 1 is 2. Okay, now log of 1 is 0. Yeah, that's a nice one to remember. So this is the natural log of 2. Okay. Okay, so here we've got sine to the power of 4x, and then we've got cos x all to the power of 5. So with these kind of examples, what we're going to take is we're going to take the trig function that has the lowest degree. So I'm going to let u equal sine x in this case. Okay, so obviously du over dx is cos x, so dx equals du over cos x. Okay. So what we actually have, so this will be u to the power of 4, yeah, because sine x is u. So always take the lowest power, okay, the lowest trig power. So this will be cos 5x dx equals du on cos x, which cancels one of those. So now we're trying to get rid of cos 4x. Now remember that cos squared x plus sine squared x is equal to 1. Okay, using the Pythagorean triad. So what we actually have, instead of writing cos to the power 4, I'm going to write it as cos squared x, all squared, okay, du. Now I'm going to replace cos squared x with 1 plus, oh sorry, 1 minus sine squared x. Okay, because obviously from here we have cos squared x is equal to 1 minus sine squared x. Yeah, recall that sine squared x is just u squared. Okay, du. From here, what I can do is I can expand this. So we get, u4 minus, so that's all squared. Forgot that squared. So that's 1 minus 2u squared plus u squared. Expanding that out, you would get u to the power 4 minus 2u to the power of 6 plus u to the power of 6. Sorry. This should be u to the power 4. And that's 8. And then that will be 6. Okay. Well, simply from here we just will integrate. So that's u5 divided by 5, 2 7 u7 plus 1/8 u, so 1/9 u9 plus c. Replacing u back with sine, so we get a fifth of sine x to the power 5 minus 2 sine x to the power of 7 over 7 plus sine x to the power of 9 over 9 plus c. Okay, so that's a little bit tricky. So some little notes. Okay. Take the lower degree, the trig function, with the lowest degree. Okay. Apply the Pythagorean identity. Resubstitute and solve. Okay, a few steps. Okay, so here we've got the integral from 8 to 3 of x plus 1 multiplied by the square root of x plus 1 dx. So I'm going to let x plus 1 be u. Okay, so if I let u equal to x plus 1, then du on dx equals to 1. And so therefore du equals dx. And sometimes when this happens, it's not the greatest, but for this example, it will work. Okay. It means that if x equals 3, so 3 plus 1, u equals 4. And if x equals 8, 8 plus 1 is 9. Okay, so what we're going to integrate is from 9 to 4. U is, so x is now, I rearrange this, x is equal to u minus 1. Okay, so I get u minus 1 on the top. X plus 1 is u, and then x plus 1 square root is u to the power of a half, du. Alright, cleaning that up, I get u minus 1 all over u to the power of 3 on 2. I can separate that, being u over u on 3 on 2 minus 1 over u on 3 on 2 du. If I fix this fraction, that's 1 minus 3 on 1.5, which is a half. And this becomes u to the power of negative 3 on 2. Integrating each, I've got 1 divided by a half is 2. So I get negative 3 on 2 plus 1. So negative 1 divided by answer, I get plus 2 and u to the power of negative a half. And I'm in my boundaries from 9 and 4. Okay, so if I use the first term, so what I could do, I could write this as 2 root u plus 2 on root u from 9 and 4. Okay, so root 9 will be 3, so 2 times 3 is 6, plus 2/3, minus root 4 is 2, 2 times 2 is 4, plus 1. Okay, so that's 6, that'll be 6 2/3, minus 5, which will give me 1 2/3. Okay. Another example. So here, this is where we want to be using tan theta is equal to t. So looking at our formula sheet, on page 2, we have the tan formulas. Okay, so it says, instead of writing sine x, I need to write the what it equals in tan equals t equals tan a over 2. So sine x is 2t 1 plus t squared, okay, using what the formula says. Okay, so what that means is that so I really should be let tan alpha on 2 be equals to t. Okay. So if I just work on the denominator for the time being, I want to multiply that by 1 plus t squared. Which gives me that. That's 1 divided by this, which means 1 multiplied by the reciprocal. So I've got 1 plus t squared over t squared plus 2t plus 1. Okay, I've just rewritten that to be a quadratic, and that's a perfect quadratic. So that what we have here is we've got 1 plus t squared on the top, and then we have this is going to be 1 plus t plus 1 all squared. Okay. Because I've let t equal tan alpha on 2, it's important to know that when you differentiate and make dx a subject, you get 2 on 1 plus t squared dt. And I think that's a good one to remember. Okay, so when using the t formula, when you take the derivative of tan alpha on 2 and make dx a subject, you get 2 over 1 plus t squared dt. So I'm going to replace dx for this. Okay, this cancels out that, leaving me just 2 over t plus 1 all squared dt. Okay, now really I should actually go back and replace these boundaries. Okay. So when x is equal to 0, right, we get t is equal to tan 0 on 2, which is 0, which is just 0. And when x is equal to 90, we get tan of 45, which is 1. Okay, so what we really should do is go back and, well, we have from 0 to 1. Okay, the 2 I can take outside, and this becomes t plus 1 to the power of negative 2 dt. which we can easily do. So we raise the power, so that's -1, so we raise the power, okay, from 0 to 1. So we have -2 on t plus 1 from 1 to 0. So 1 plus 1 is 2, so that's going to be -1 minus -2. -1 plus 2 is 1. Okay, so let's recap how we did this. So obviously we let t equals to tan x on 2, or theta on 2, half of it. Use the substitution for sine or cos or tan using t formula. Okay, simplify. Note that t equals tan x on 2. So dt on dx is equal to 2 over 1 plus t squared dt. Okay, and then solve. And that's it.